Okay, so what we're going to start doing now, we started looking at this a little bit yesterday when we started talking about the magic secret formula that you can use to take derivatives is instead of taking the derivative and thinking of it as the slope of a curve at a particular point, we're going to start thinking of the derivative as a function of its very own. So instead of being a number, it's a thing with x's in there that you could actually graph and draw and all that fun kind of stuff, okay? And this is a tough conceptual leap to make, but what we're going to do is we have a graph of a function right here, and below it down here we are going to make a graph of the derivative of that function, okay? So this is the actual graph. This is going to be a graph of the slope of this graph as it moves from left to right. Yes?
I spaced it. I'm in the assembly group for leadership.
Oh, okay, that's fine. We're recording this and you can watch it at home, all right? Okay, so if we start over here on the left-hand side, what kind of a slope do we have on our graph here? Negative, okay? Very negative, mildly negative, somewhat negative, so-so negative. Okay, what happens to that negative slope as we move from the left to the right? It ends up being 0 right about here because we have a horizontal tangent right there, so we know that that's going to be 0 on the graph of the derivative, right? So as the slope goes from left to right here, it starts out being negative, but then it gets bigger and bigger and bigger and bigger until it reaches 0, okay? So the graph of the derivative would start somewhere down here, negative, and then it would go up to this point right there. Okay? What happens to the slope as it gets past this point where it was 0? It becomes positive, and it becomes more and more and more and more positive, right? Okay? Still positive right here, so it's increasing all the way up to about there, right at about 1. It's increasing really quickly, and then what happens once it leaves this point right here? Is it still positive? Right past this point, is it still positive? Yes, it's still positive, but it's less positive than it was over here. In other words, this line right here has a steeper slope than this one right there, okay? So it gets increasingly larger and larger and larger, and then when it hits that point, it starts to slow down a little bit and go back down. So it's going to turn the corner and go back down here until what happens right there? It is 0 again. So I'm going to have another place where it crosses the x-axis right there at 0. So it goes up, 0, comes back down. Okay? Now what's going on with this slope here?
Down.
It's down, so it's negative. Okay? So it's going to be down here in the negatives. Let's pick an easy point. This is the zeros are the easy ones, right? So at x equals 3, the slope is 0 again. So this is the same thing going on over here as we have with this guy right here. It starts out being not very negative. It gets steeper and steeper and steeper until it gets to about, maybe there. Does that work for you? And then right about at that point, it becomes less negative. So it turns the corner. It's still negative all this way, right? But it's going to turn back around and start going back up to 0. Okay? And then what happens to the slope as I continue here from the left to the right? Yes, it's going to be positive, 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 positive. So this is going to go off something like that. Okay? So I know that's kind of hard to connect those things if you haven't really thought about that very much, but there's some key points here. These points right here are the easy points because those are where the slope is 0. Okay, so it's changing from being negative to being positive. And so those will correspond to points at, where it crosses the x-axis. Does that make sense? And then these other points right here where it changes from being increasingly positive to decreasingly positive, or in this case right here, it was getting more and more negative, and then it started getting less and less negative. Those are very important points that we're going to spend a lot of time talking about later on in this class. Those are called points of inflection. And what on the graph of the derivative corresponds to those points of inflection? Yeah, right, good, excellent. The maximum right here happens at this point of inflection right there, because that's where, at this point right here is where the slope is most positive, okay? And then after that, the slope starts to tail off a little bit, and then this is a minimum right there, because at that point of inflection, that is where the slope is the most negative, I guess. And then after that, it starts to become bigger and bigger, okay? So if you can find those key points, if you can find this is a 0, this is a 0, this is a 0, point of inflection, then you can just kind of connect the dots and you're good from there, okay? And so this stuff right down here, how high up I go on this and how far down, that's just an estimate. So the main idea is that we want the shapes of the graphs to match, okay? All right, so let's do a quick and easy one since we now have a magic rule. Okay, so let's start with f of x equals x cubed minus x, and you could do this by plugging in x plus h, right? Taking the limit as h approaches 0 and all that stuff.
I'm not there.
Secret formula tells us 3x squared minus 1, because this is x to the first power. So the 1 goes down in front, and then you take 1 off of the power, which gives you x to the 0, which means it's not there anymore. Okay? All right, so let's look at the graphs of these two things and see how they relate. So the first one was x cubed minus x. And then you're telling me that the derivative of that is x squared minus 1?
3x squared.
3x squared minus 1? Nick. Does that mean yes to that?
Yep.
Okay, so let's see if that matches up with the points that we were talking about in the last problem. I'm going to zoom in a little bit here and see what's going on right in the middle. So let's go negative 2, 2, and negative 2, 2. Okay, and then we'll look at the graph. So here's the original graph. So we talked about this point right here being an important point because that is where the slope is 0, right? And you'll notice that the graph of the derivative crosses the x-axis right there where the slope is 0, as we expected. The point of inflection is sort of right in between these high points and low points, that thing right there, okay? And so the slope is getting more and more and more and more negative until it hit that point of inflection, and then it started getting less and less and less negative. So this point of inflection corresponded with what Tyson called the minimum on the graph of the derivative, right? And then we have another place where the tangent line would be horizontal, so the slope is 0 right there again. And then from here on out, the slope is increasing and increasing, and so this graph is increasing and increasing as well, okay? And of course, you all recognize this as a cubic. And since the derivative, you bump the power down by 1, that means that the graph of the derivative of a cubic is going to be a quadratic, okay? All right, so let's do another one that we can't necessarily use our secret rule for, but we've done this before. Let's start with f of x equals the square root of x and find the derivative of that. Okay? So now, like I said, because we don't have power, we're going to have to do it the old-fashioned way. So I'm going to take the limit as h approaches 0 of what? This is the part you have to know, this little formula. Right, root x plus h. First thing you do is plug in x plus h into the formula, minus root x, the original formula, and that's all over h. Okay? So in order to find that limit, what do I have to do?
Wait, is that H?
Yes, the h is under the root 2 because I'm plugging x plus h in for the whole thing. Okay? What do I do to evaluate this limit? Conjugate? Okay? So first times first, the square roots cancel and give me x plus h. Inside and outside cancel, and then negative square root of x times positive square root of x is negative x, right? And that's all over h times root x plus h plus root x. Oh, and that's all over, oh no, h is like this, okay. So what happens with the x and the x? Cancel out, so that gives me h over h times root x plus h plus root x. What happens to the h's? Cancel. You guys have your own foreign language. Means cancel, and eight means yes. What was the noise you made? I thought that was a no. What do I do now that I've canceled that h off the bottom? Plug in 0 for h, and so I get 1 over 2 times the square root of x, right? Is there a way that we could have found that answer using our secret rule? Can I write the square root of x with an exponent? What would the exponent be? X to the 1/2. Okay, so if I have x to the 1/2 and I follow our secret rule, what do I do with the 1/2? Put it in front. And then that's times x to the what power? Negative 1/2 because I have to subtract 1 from the exponent. But what is x to the negative 1/2? Square root of x, but on the bottom. So this is 1 over 2 times the root of x. Okay, so you can still use that secret rule right there. You just have to recognize that as a exponent instead of a square root. Okay. All right, so let's take a look at these graphs to see what's that. We had a couple of kids that played pretty well, so I felt better about that than our Lucenter debacle. But we still lost.
You got played?
Not too bad, about 30. I just took the varsity kids.
Who did you go up against?
Kalama.
You shot the highest.
Their coach totally. Okay, so here's the. Ooh, that's not a very good view. Here's the graphs of. This is the square root of x, and this is 1 over 2 times the square root of x. Let me change the window so we don't need any negatives here. We don't need no stinking negatives. Okay, so there's the square root function, and then here is the other one, and you really can't see it for most of the thing, because what's happening, what's the slope of this square root function right here at 0? Like, I mean, right here it's getting flatter and flatter and flatter, so you can see that as you continue out this direction, the slope is getting closer and closer to 0, so that's why this goes right down there where you can hardly see it. What's happening right here? If I'm going this way, yeah, it would be increasing. What would be the slope right there? 1 would be maybe somewhere right there. This is super steep. Yeah, it's not going to be negative infinity, it's going to be positive infinity. It's almost infinite right here. So this, because the tangent line right there is almost going to be straight up and down. So the graph of the derivative starts way up here. You can't even see it, it's so close to the y-axis. And then as this graph starts to level out, the graph of the derivative starts to get closer and closer to 0. And so it looks something like that, okay? So there is a visual relationship between the original function and the derivative. It's a little bit tricky, but you know, you can see it. All right, so brief little history lesson for you. You guys know who like discovered calculus, sort of?
Calculus.
A bad person.
Calculus himself.
This was all came to play by your old friend Isaac Newton, who has not only made your life miserable in physics classes, but also in math classes as well. So if you do ever invent a time machine and you want to go back and kill someone, maybe not Hitler, just take out Isaac Newton and school will be much easier, okay? So he did all this stuff in England and figured out all this stuff, and then he published it. And then this German guy by the name of Leibniz, after Newton published his work, Leibniz said, oh wait, I figured that out like 5 years ago and I just didn't tell anybody. And yeah, so they had a big like math battle, like it was a major, you know, big deal to figure out, you know, who actually figured this out, who came up with calculus stuff.
Rulers, that.
And so, yeah, it says in here there were followers of Leibniz and there were followers of Newton. So, you know, it was this whole big deal, and then it seems like they both actually did it independently. That's what we're going with. But the bad news for you is since two different guys invented it, there's two different notations that you can use. So Newton came up with this prime notation. So you can do f prime of x or y prime, which is what we've been doing. Leibniz, because it's the slope, he went more with the change in the y over the change in x. So his notation is the dy dx or df dx, or another weird way that you can write that is like this. So all 5 of those things mean the exact same thing, okay? F prime of x, y prime, dy dx, df dx, d dx of f of x all mean the derivative. Yeah, I mean, so for your own use, this is probably the easiest one, but you're going to see these different notations in your homework assignment, so you need to recognize that they all mean the derivative. Do you see where the dy dx comes from? Because the slope is the change in the y over the change in the x, right? And in science, yeah, exactly. And in science class, it's delta y over delta x, and so you went with dy dx to stand for the delta. So all of those just mean take the derivative, okay? And what's that? Have you killed 2 people? I'd just go with Newton. He was just kept it to himself forever. Been good. Okay, so then the last thing that we need to know about this is that there are some ways that the function can be non-differentiable. Non-differentiable. Yep. How it can fail, how a function can fail to be differentiable. So next time you're playing Hangman, so that word right there, differentiable. Okay, so if you think about the fact that we are finding the slopes of tangent lines, one of the ways that a function can fail to be differentiable at a particular point is if you have something that looks like that, and that is called a corner. So at this point right here, the derivative would not exist, okay? Because you've got a kind of a tangent line going along there, and then at this point right here, how would you draw the tangent line? Would it be like this, or like that, or would it be 0, or, you know, it's hard to say. There's a lot of different points that you could put there that would represent the slope of the graph at that point. And also the graph of the derivative would be nice and smooth right here, like it's going positive, 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 and then all of a sudden, wham, it changes and now it's negative. And so there would be a break in the graph of the derivative. And so right there the derivative does not exist. Okay? It could also fail to exist if there is a discontinuity in the graph. Nope, that's not it. There. There's a discontinuity there, you can't take the derivative. Okay, possibly. There are situations where that'll work, but it's something that we have to check to make sure. And then the other one is kind of a weird one because in one sense it does exist, and that is if you have a graph that has a vertical tangent. So if I drew in the tangent line right there, it would be straight up and down. But what's the slope of a vertical line? Yeah, undefined. So at this point, right there, then the derivative would not exist either because the slope right there is undefined. So that is a, yeah, because there's only one point right there. You know what I'm saying? It's like coming in there, and then there's one point right there where it's vertical, and then okay, so technically it doesn't fail the vertical line test, the function itself. So that's how that would work. Okay, so one example of where that might happen is if you look at the absolute value of x. Do you know what the graph of the absolute value function looks like? Yes, it is the v. Okay, so where would the derivative of this function fail to exist? The left is good. What's the slope of the tangent line all the way here? -1. So if we graph the derivative of this function from -infinity to 0, you would have a line at -1. What's the slope of the tangent line on the right side of this? +1. So from 0 to infinity, you would have a line at +1. So where does the derivative not exist? At 0, because there's a corner right here. So the slope jumps from -1 up to 1. Okay? So that's an example of a corner that you would see on the graph. And these are double open holes right here, double open circles, because it doesn't exist at either one of them. Okay? Okay. Seems like you guys were kind of chatting about this yesterday. Why stop at one derivative when derivatives are so much fun? So we can use our magic secret formula like we did before to find the derivative of x cubed minus 1, and that is 3x squared minus 1. Now I can take the derivative of the derivative, and that's the old double prime.
6x.
So the derivative of 3x squared minus 1 would be 6x. Okay, the 1, you have to think of it as 1 times x to the 0. So if you move the 0 in front, what happens?
0.
It's 0, so it's gone. So the -1 just disappears. And then you could take the derivative of that if you wanted to. That would be what? Just plain old 6. And that should make sense if you think about the derivative as the slope. Y equals 6x is a line, right? With the slope of 6 the whole time. So that's why the derivative comes out to be a constant value there. And then you could do that one more time if you wanted to. What's the derivative of 6? 0. Okay? And again, if you think about what the derivative represents, what does the graph of y equals 6 look like? Horizontal line at y equals 6, and so the slope of that line all the way across is 0, so the derivative is also 0. Okay? And then you could keep going if you wanted to, but that would be really stupid because they will all be 0 after that. Okay? All right?
Right.
That's all I got for you.
Can't do it.
Can't do it?
No.
So you'll be studying.
We gotta study this week.